Okay, recording just started. So take care with your comments. Fine. So for the written exam, what you should manage is course material, the files I'm uploading, and also the discussion we have during our classes, and those 3 papers as indicated here on the screen. So that's relevant for the exam on Friday. Okay.
So it will be like that you are like that you are pointing out some questions and we have to answer, or if you like, do we also have to use the program R?
You don't have to use R. The written exam is just question answers.
Okay.
And I want you to show me that you understand what we have been doing during this week. So I'm not asking for details because it's open book. So it doesn't make sense to ask for details because you can look up details in the internet or wheresoever. I ask you for understanding of the context.
All right.
That makes sense? No details, no R, understanding of the material.
Okay.
Okay. Group project, and now Tobias, we are coming back to your question. Please build a group, 3 or 4, hopefully diverse, but up to you, and pick some social network. The next page, on the next slide, I put some examples, but you are free to pick your own social network, some ideas of previous projects of previous versions of this summer course were all of you. So one group had the social network with all of the participants of this course, or all of your classmates during last year or last semester, or your Facebook friends, or whatsoever. Okay, so if you are in a football team, you can use your own data as social network. You can also get data from internet, what you want. So you're free to pick your social network. I'm going to ask you to use software to analyze your social network. R is one option that has been announced, but if you feel more comfortable with other languages, Python or any other language, that's fine. So the programming language is not an issue. And the particular analysis I'm asking you is to do community detection. What that means, that's part of our course. I think, well, today we're going to speak somehow about community detection, and we will see some more detailed techniques for community detection and also software code during this week. So what I'm asking you is to pick your social network, create and analyze it, and do community detection. That's basically the group project. And again, as you can see now on the screen, act as a consultant for your client. Okay, so let's say if you analyze, or let me mention another project I saw last year. Students chose airports as a social network. So the node of a social network was an airport. The links between those nodes were flights. And by doing some community detection, they could somehow identify airports that are similar to each other with a lot of interaction between airports. We'll come back to that later, but try to analyze your social network and try to present some idea for decision making. So what's the decision your client would like to take, and how can you help your client to take a better decision based on your analysis? Okay, I know that's not clear, that's not precisely defined, but that's part of the project. So let's say that's part of life, where your client does not always define precisely the project. It's up to the consultant to define the project. It's up to the consultant to convince your customer. Your client mentions some problem. So I would like to improve my sales figures this year, but not in more detail. So it's up to you to define the project. It's up to you to convince your client with your solution. Okay.
I've got one question, if you can understand. So we can also take, like, for example, a company like Microsoft, and then we can analyze their social network with, like, analyzing if it's a hub and spoke network, if it's centralized, if it's integrated, and then use the centrality measures to see the degree centrality and, like, give advice to the customer how they should integrate themselves in their network.
Okay, Tobias, thank you very much. That was already your presentation. Well done. Well, the answer is yes. Yeah, okay. You can choose the network you would like to analyze. You have to convince your group mates with your idea. So you have to come up with one solution for the entire group. It shouldn't be your own work, just your work. As far as I can understand from your comment, you do already have some experience, or you do already have some network in mind. That's fine. So maybe some of the attendees want to join you in your group. That's fine for me. Yeah, you can choose your own social network. What else? How do we evaluate this project? There will be a presentation on Friday. As we can see here, 10 minutes. I think it's going to be less. 5 minutes would be fine, but I'm not very strict on that, so it depends a bit. How many are we? We're 10 groups. Yeah, between 5 and 10 minutes each group. And a written report, which I expect you to send me by October 1st. Okay. Any doubts so far?
Question on this in the report. Is the report an individual task based on the group work? Or
no, one report per group. Please think of my time. I have to read all reports. So one report per group, and hopefully not too many pages. But okay. We'll come back to that later. So intentionally, I don't work with, how would you call it? Miri, ¿puedes ayudarme? Una rúbrica. ¿Cómo dirías una rúbrica en inglés?
Rúbrica.
So I don't know how to call it in English. I don't like to work with a scheme. I don't want to provide you a scheme for the report. But
un esquema.
Esquema, no? Scheme.
Mm-hmm.
So I don't want to define a scheme, because I think that's part of your work, to define the scheme of your project, of your report. So I don't want to tell you 1 page description of the problem, then 1.5 pages, and so on. It's up to you, but I would like to limit it not more than 5 pages without counting figures. So pure text, not more than 5 pages, something like that. But if you need 6 pages, it's fine. I'm not that strict in that issue. Okay. Any other doubts? And if there will pop up some doubts tomorrow or the day after tomorrow, of course, we can discuss it. But that's basically what I would like you to do in the group project.
Maybe one more question. Is it more about how we worked on our project and how we approached the whole task, or is it more like a document which we would give to a customer, so where we sell our idea?
You're my consultant. I'm hiring you, so it's up to you. I don't want to tell you how to do your work.
Okay,
Moritz?
but so you get the report as our customer and not as Richard.
Right. I'm your customer. Please convince me, and bear in mind, there are competitors. Yeah. So maybe you have to compete. You have to convince me, because I could do the same work with another consultant.
Okay, thank you.
Yeah, welcome. Any other questions? Okay, and since I know that it's not that easy to find a social network within 1 week, so I'm aware of that problem. That's why we will have a spare time on Wednesday afternoon where you can work with your group. So there will be no classes Wednesday afternoon. I think it's German time between 4 and 6 p.m. Okay, there you can do your group work. And I understand that 1 week is not enough to find a social network, to do the analysis, to present. So it's a tough work. Welcome to consulting. Okay. And that's why I offer here some data sets. If you don't have, as Tobias, if you don't have a data set, Tobias has already a data set in mind. If you don't have some in mind, here are some web pages where you can find network data. You can just jump into these websites and find some network data. But again, you're free to define your own social network. And that's it regarding evaluation. Any doubts? Mari?
Yes, just one comment. I think the second link is not working perfectly, so maybe you can have a look and maybe fix it. At least I tried to click on it and it didn't work when I reviewed the presentation.
You checked it already?
I think it's just about the dot. So it's www.personal, maybe.
Of course. Here there should be dot instead of dash. www.personal. I guess I didn't try it, but yeah, it makes a lot of sense to me. So let me do it online. Anybody faster than me in trying? It doesn't work either. Okay, don't know what to tell you. Net data. Okay, let me check and I will update the link. The second one does not work, even with the dot here instead of dash. But anyway, it was just one option. There are plenty of network data. So it's not necessary to have the second one, Mari. But anyway, I will try to fix it maybe today during our break or today after our session, after our final session today. So I will update this link. But the other links, they have plenty of network data.
I think somebody posted actually a correct link already. So, but I think it had 2 dashes in the PDF document that you posted. So, could be that was the problem. So
Eric said, with the dash it worked. Well,
yes, but not from the PDF doc. So you posted it online, the presentation, and I just went through the links, and I think the one that was posted, it had 2 dashes in there, and somehow the link was broken. But this link that Eric has posted works for me as well, so all good.
Okay, just checking. Yeah, it worked. Okay. Yeah, that's fine. So that's evaluation. Any other comments so far? So let's start with the content. Let me just think if something else is missing. No, okay. So during this week, we're going to speak about how to represent a network. What does it mean, a social network? What are the elements to build and represent a network? One particular application is community detection. Think of a social network, for example, your friends in a social network, Facebook or Instagram. What are the social networks you're using nowadays, Mari? You're on which social network?
Oh, I mean, many LinkedIn, Instagram, Facebook, definitely.
Still, Facebook
Twitter.
is still an issue?
What do you mean an issue?
It's still a social network you're using?
Yeah, sure. I mean,
Okay.
all the events and everything that will be, yeah, it's a social network that I'm using.
I thought, I had the impression Facebook is already old-fashioned for another generation, but you're still using it. Okay, fine.
Maybe I'm an older generation. I'm not so young anymore.
What about TikTok?
I'm not using it.
Yeah. There's a big issue with TikTok now. Donald Trump wants to ban it, but that's another issue. Maybe we can analyze the TikTok case later this week. Okay, so we'll go into community detection. You can analyze a community. We'll first understand what is a community within a social network, and then we'll understand how to identify, how to detect communities. And that's part of the project where I ask you to apply community detection to your social network and to propose some decisions. So I always put very much importance on the decision-making aspect. So this is not about having the best technique. This is about decision-making based on a proper analysis of available data. So the more generic term is graph mining. We will understand a social network as a graph, and we will do data mining on graphs. We will also speak about privacy issues related to social networks, and we will see a couple of applications. And during the last class this week on Friday, I will mention some of the challenges we have in research. For those of you who are interested in going into more detail regarding research on social network analysis. So that's, let's say, those are some of the topics we will address during this week. As I said before, the mathematical foundation is graph theory. And what you can see here in this image is a picture of the city of Königsberg, where you have the river and 7 bridges. And Leonhard Euler, back in 1735, defined or came up with the problem of the 7 bridges in Königsberg. And who knows what he said? Who knows this problem? Who knows what this problem is about? Any volunteer? Any idea? No?
Fastest way to basically cross the bridges, so to optimize the path. Yeah.
Well, is it about optimizing, Gurang?
More or less to complete the whole circuit in the minimum amount of time. So I guess it's more of a time optimization problem.
So what you have in mind is the famous traveling salesman problem, which is well-known problem in operations research, management science, okay? But that's not the issue. Any other comments about the problem in Königsberg? So let's do the following exercise. Let's visit Königsberg and let's find a tour crossing each bridge exactly once. Who comes up? Who is first to come up with a solution? How can you visit Königsberg crossing each bridge exactly once? So maybe I can start. You can see the cursor on my screen. Yes or no? It's moving here.
Yes.
Yeah. Yes. So let's start here. we cross here, then we cross this bridge, we go back, we cross this bridge, and then we are here. Okay, end of the story is Leonhard Euler found that it's impossible to cross each bridge exactly once. Of course, without getting wet, without swimming, without using a helicopter and so on. So it's impossible to cross each bridge exactly once. And based on this problem, he started a discipline which today we call graph theory, which is a famous or an important discipline within mathematics, within pure mathematics. And there he defined, he kind of came up with a abstract model of this problem. He said, okay, I don't want to analyze bridges and streets. I want to analyze something more abstract. He defined bridges as nodes. Okay, so each bridge is a node, and between bridges we have links. So from this bridge I can go to this, and this bridge. So he defined what today we know as a graph, which consists of nodes and links. Those are the building elements of a graph, nodes and links. And that's how we can define a graph. And we will later see how to understand a social network as a graph. Okay, so that's where it started. There are some examples. I go through this quickly. Mark Lombardi showed some relations among people as a graph, where again we have nodes and links. Here a node is a person, and links among persons are built if there is a social relation between those two. Okay, I'm not going into detail. There is a Wikipedia page where you can find more details. Just want to mention some social networks. There is one social network from Lima, the capital of Peru, where we well, that's actually from a newspaper. In that newspaper, they published a group of money laundering where we had the boss, okay, and people working for him. So we could identify people as nodes, and the links between nodes are established based on their relation. So there is a relation between everybody on this social network with the boss, but also links among some of the members. So that's how we can understand a criminal group as a social network. Okay. Some words about social networks versus social media. There are plenty of social media. Some few of those are social networks. It's hard to read, but down here we can see social networks, the word social networks, and where we have Facebook and so on, other social networks. But there are plenty of social media that are not considered as a social network. Just to define the terminology, Facebook network, okay, again, there are nodes which are Facebook users, and links are shown here by, let's say, this slide. And we can see where is the concentration of Facebook users. Those are kind of communities, so we can understand some communities where we have high level of interaction. That's the first, let's say, abstract understanding of what a community is. High interaction among users, like here or here. That would be Sao Paulo, Rio de Janeiro, East Coast, West Coast, and so on. But also different applications. We don't have always people as nodes and relation among people as links. So here I'm showing a social network of recipes, and we can, as we can see, there is a high concentration among these recipes and also a high concentration among these recipes on the right side. Any ideas? What are we speaking about? How did we establish this social network? How did we define nodes and links among nodes? Now we can see here there is one node, it's called salt. There's another node which is called onion, another node which is called butter, and there are links among those nodes. Any ideas? How can we define a link in this social network? Some cooks among you?
Maybe as a combination of 2 ingredients in a recipe.
Very good, very good. So if 2 ingredients go together in one recipe, then we establish a link between those 2 ingredients. Moritz?
Yep.
Okay. You like to cook?
Yeah, from time to time.
Yeah. You prefer eating? Me too.
Yeah.
Okay. Anyway, so what can we see here? We have ingredients. Those are the nodes. We did analyze many recipes, and if we find a recipe where 2 or more ingredients go together, then we establish a link between those ingredients. That's the way how we established this social network. The size of each ingredient, of the word representing each ingredient, represents the frequency. How often did this particular ingredients appear? So that's the size of each word. It's proportional to the frequency. And what we can see here on a simple view is there are many links among those ingredients on the left side and many links among the ingredients on the right side. And those are what we later will call communities. We have a community in this social network. As you can see here, I have social networks of recipes. So there is a community on the left side and a community on the right side. And why, what do you think? Why do we have exactly these 2 communities? Which kind of recipes do we represent here in each community?
Yeah, on the left-hand side you have rather the sweet stuff, and on the right you have the salty ones.
Yeah. Which one do you prefer, Katharina?
I would prefer the left side.
Okay, great. I like both, but
yeah,
it depends.
Me too.
Yeah, sure, I know.
First
Mari.
the right side and afterwards the left side.
Exactly, exactly. The right side with a good glass of red wine and the left side with a good coffee. Speaking about coffee, thank you very much.
Why doesn't salt have a link? I don't see any links on this graph. I'm just wondering if there's a reason.
Very good question. To be honest, I don't know. Yeah, excellent question. Of course, salt doesn't appear by its own. I don't know the answer. But very good question. I think it's I won't say it's an error. Maybe on purpose they said salt has so many links, so we don't show the links. That's my explanation. I found this figure on internet. I don't know how they developed the social network. Let me see. There's one comment on the chat. Could be what Christian says. The link is too fine in this image. Could be. My answer is just I don't know.
Maybe
but anyway,
maybe they wanted to show the left and the right side, and if you would have the connection to the salt, you wouldn't see the clear difference between both sides.
Could be. Good comment. Could be. And anyway, so this figure helps me to show first how communities would look like. That's a set of nodes, ingredients in this case, with a high density of links. And here we do see the links. So the question remains, why does salt have any links? Again, I don't have the answer. But anyway, so here we see a high density of links. And during this course, we will define formally what does it mean, density. Same on the right side. So we identify some communities. That's one message we can take away from this figure. And the second message is we should think out of the box if we think of social networks, and social networks, as the word says, is not always a way to represent interaction between humans. So in this case, we have interaction between ingredients. Of course, there is no social behavior of water or salt or whatsoever. But anyway, the social network analysis is a tool to analyze recipes. So I would like to tell you, or I would like to ask you to think out of the box, to use social network analysis not only for social behavior. So we can use the same tools also for different kinds of networks. Just a second, let me see how we are advancing. Okay, 7:20. Another one, so there is a web page called Node XL, where they have some, you can upload some social networks. Let me go to this web page. You can do the same online. So I'm just opening this web page to show you what we can see here. Going to share the screen. So now I guess now you can see my screen, Node XL graph gallery. Okay. So first of all, the website, Node XL is a website, interactive website where you can upload your own social network. Okay. And you can analyze it this way. Let me explain first what we are seeing here on this graph. So that's a network which has been uploaded on Saturday, September 12th, just 2 days ago. And it's about I5 fire. So I Googled it and I found the fire on a interstate highway, Interstate 5 highway. There was a fire on that interstate highway. That's why I put the image with the fire on the PowerPoint slide. So there were Twitter accounts that mentioned the I5 fire in their tweets, and those are the most relevant accounts, Twitter accounts. Top hashtags: Oregon fire, Talent Phoenix, Medford fire, okay, whatsoever. Here we have a description of what the graph is about. This graph represents a network of 681 Twitter users with tweets containing I5 fire in their tweet. So these tweets were taken from a set of 18,000 tweets. It was built on Saturday, September 12th. Okay, so nodes are Twitter accounts. Edges, I will use edge and link interchangeably. So edges or links are built if there is reply to. Okay, so there is a link between two Twitter accounts if one account replied to another account. There is an edge for each reply to and another edge for each mention. The graph is directed. That's a notion we're going to introduce during this morning. The graph vertices, okay, vertex or node is a concept, are terms that I will use interchangeably. Nodes or vertices are grouped by cluster using the Closet-Newman-Moore algorithm. That's an algorithm we will introduce during this week. So that's one of the algorithms to do community detection, and you're free to choose to use this algorithm or any other algorithm for community detection. And there is a algorithm for layout, to lay out the graph, to decide the particular layout of the graph. That's where they used this particular algorithm. We're not going into detail regarding layout algorithms. Okay, And from here on, you can see some graph matrix. So they have 681 vertices or links. There are 801 unique edges or nodes. Okay, in total 185 tweets and so on. So those are some metrics describing the graph and so on. So there is, and then there is an analysis of each first of the entire graph. Those are the top URLs in the entire graph. And then they analyze communities. G1 is the largest community, G2, G4, and so on. Those are communities, as you can see here, G1, fire, I5 closed, and so on. That's one community, and we have plenty other communities. Okay, so I just want to mention this case. Let's go back to the PowerPoint presentation. Which we have here. Okay. So we saw the web page, community detection in this case, and that's a picture of the fire on the I-5, Interstate 5 highway in Oregon. So here, one node is a Twitter account, and links between nodes are established based on reply to or mention on Twitter. And what you can do is by yourself, you can open a free account on this web page, and you can upload your own social network and do the analysis on NodeXL. I didn't do it yet, but as far as I could see, that's possible on this web page. Some historical remarks. Social network analysis, of course, nowadays it's very much related to social media like Facebook, Instagram, Twitter, and so on. But it has a long history. Back in the 19th century, Comte and de Tocqueville started with some first attempts to find structural principles in social networks describing the relation between humans. Georg Simmel in 1908 spoke about the relations between strangers. He said, a stranger is someone close to us, okay, insofar we feel between him and ourselves, but at the same time, he or she is far from us, since it's not a common contact, it's not a close friend. So there we have the first notion of distance. How can we measure distance in a social network? That's one of the important aspects. We will come back to that later. Then maybe one of the first studies, formal studies of a social network was the famous class of 1880, 1881. That's a friendship network of a German boys' school class. That's what we can see here. The professor at that time, Johannes Delitzsch, he analyzed the relation among the students of his class. That's a symmetric matrix where rows and columns represent students. So we have 50 students in one class. Amazing, isn't it? But that's how it was at that time. So 50 students in the, and each student represented in a row in a column. And in the off-diagonal elements, Delitzsch mentioned the relation, the interaction between students. Of course, the diagonal represents or is empty, because that would be the relation between a student with himself, because it's just a boys' school. And off-diagonal elements show how they related. There is a plus or minus or some marks in each cell describing the relation between those boys. I don't know exactly what it means, and I don't want to go into detail, just want to mention some historical remarks that this one is considered one of the first formal studies of social network analysis. Okay, 1880, 1881. Then Stanley Milgram performed the experiment, which later he called and we know as the 6 degrees of separation. Who knows what this experiment is about? Any comments, ideas?
Football?
Not exactly, not exactly. Okay, I put this image with Messi. Well, there he is younger. He doesn't look that young nowadays. He's still wearing the shirt from Barcelona. By the way, he's going to stay in Barcelona. What are your opinions? He's going to change? He's going to leave Barcelona?
He said that he's going to stay.
We still don't know. Katharina, you said he's going to stay?
Yes, he told last week, he told that he is going to stay until next summer.
2021?
Yes.
Okay.
And then he's coming to Bayern München.
If he wants to win the Champions League, that would be a good move. Or he's going to Japan? Yeah, that's another issue.
The contract is not allowing to go.
Going back to Argentina? No. This experiment is not about football. I with this figure, I just want to show that each one of you is on average 6 degrees of separation close to Lionel Messi. But in the year 1967, Stanley Milgram had some other ideas in mind. Who knows about the experiment he performed? What was it about?
Is it the Milgram experiment? Where you have to remotely decide over a decision from another person? So it's a psychology experiment, is that correct?
It was an experiment. It was about psychology.
I think Christian remembers something, but Milgram's objective was to find out if a letter sent to a complete stranger, if it can arrive to the destination without knowing anyone, and how many steps will it require.
Yeah, very good, Semad. So he sent many letters, don't have the exact number, and each letter he sent it to people within the United States. So that was not worldwide, but within the United States, and he told each recipient of the letter, please make sure this letter arrives to some other person within the United States, but arbitrarily chosen. But don't find him or herself, him or her on somehow, just send this letter to someone you know and ask this person to do the same. And once the letter arrived at the person where it was supposed to arrive, this person had to send the letter back to Stanley Milgram. And then he counted through how many people went this letter. And on average, it went through 6 people. That's how he came up with the famous notion of 6 degrees of separation. So he said, in order to make that a letter sent to one person arrives at some other person, it has to go through 6 people that know each other. Okay, so on average, it was 6. In some cases, it was just 2, maybe. In other cases, it was 20, but on average, it was 6. Said that this experiment was performed just in the United States, sending letters. Okay, and nowadays, of course, it's much easier. We have the 6 degrees of separation among people that know each other, for example, on Facebook, Twitter, Instagram, other social networks. And theory tells us that the number 6 is going down worldwide. So we are much more connected than during the 60s, which is not a big surprise. Okay, so again, it's speaking about nodes. it's speaking about contacts, it's speaking about distance. Those are concepts we're going to introduce during this week.
But what about Lionel Messi?
Excuse me?
What about Lionel Messi on this page?
I just put one person I like on that screen to tell you that each one of you is kind of 6 degrees of separation close to Lionel Messi. Okay. But the experiment, of course, it's not about Lionel Messi. It's not about football. Okay. It was performed in 67. So you can change Lionel Messi by any other person. Okay.
I want an autograph if anyone knows him.
Excuse me?
I want an autograph if anyone knows him.
Me too. Just let me check. There was a comment on the chat. It's not the Milgram experiment. Of course not. Lionel Messi now is 31, 32 years old. So he did live in 67.
Do you know a study that actually shows how the connectedness or how the distance, how the connectedness goes up, how the distance or the number of nodes reduces? That is a kind of longitudinal study that actually shows this path. Because I heard like this 6-figure actually has been confirmed through I think a study on Facebook that everybody knows everybody on this planet on average through 6 nodes. Would be interesting to see how this developed over time, or is there a study or something that investigates it?
I heard about a study like this. Actually, that's what I mentioned before. The number 6 now, the number degrees of separation is going down. It used to be 6, and now it's going down. So I understand there is a study. I don't have it right now, and I don't know exactly where it appeared. So if someone of you knows about this study, maybe you can share it on the Moodle platform. Okay. Yeah, did I make myself clear? I don't have any better answer to your comment. Okay. So with this slide, I would like you to work in groups, and maybe that's a first break we can have. I would like to exercise, I would like to practice the identification of social networks. So remember the recipes, which was kind of strange social network. So here I'm mentioning some applications, and I would like you to do a job within a group identifying social networks. Let me give you the first example. So now I'm going to speak about churn prediction. Let's think of a telco company. A telco company is suffering churn. I guess everybody of you knows what churn is. People leaving the company, just quitting the contract. And that's, of course, a major issue for companies. So they want to avoid churn of good customers. I'm not referring to bad customers. Maybe in the case of bad customers, you prefer the churn. In the case of good customers, that's a concern for all companies. If good customers are churning or leaving the company, maybe by stopping the contract. In the case of a telco company, for example, we could think of churn as customers that are switching to competitors, so that are leaving the particular provider. And there are plenty of models, let's say traditional data mining models for churn prediction that take into account just personal attributes of the particular customer, maybe his or her age, income, calls, and so on. But just on an individual level, a model that decides for each customer based on their individual data. That's churn prediction, which is a traditional approach in data mining. How can we extend this kind of models using social network analysis? So we can analyze the call behavior among customers. We can model our social network in the following way. Nodes are customers, and links are established. How do we establish links among customers? In this particular case?
Maybe if there is a commonality between the attributes of two customers, then there is a link.
There is what?
Then there would be a link.
I didn't get the first part of your command.
So if there is a commonality, so if they both have, if they both are between 18 and 20 years old, then there would be a link.
Okay, got your point, but that's not what I'm stressing with this example. In this example, I would like to stress that behavior among nodes is modeled. Phone calls, okay? In the case of a telco provider, I'm establishing a social network using customers, my customers, as nodes. And if they call each other, then I'm establishing a link between the two customers. Okay, nodes are customers, links are represent phone calls. Okay, that's the way I establish my social network. And with this kind of a social network, I can improve churn prediction models, which traditionally use personal data and no interaction among two customers. The idea behind this social network analysis is that people that are churning somehow affect their contacts. So if I'm not happy with my provider and I want to move to another provider, then maybe I mention my intentions to my friends when I'm calling them. So maybe they can get kind of infected by my intentions. So the social networks kind of propagates the intention of some people. Did you get the idea? So a telco provider is concerned about churn. There are traditional data mining models for churn prediction using just individual data. You can improve those models, establishing and analyzing a social network, which is built using customers as nodes and phone calls among customers as links. Okay, Goran, please.
My question was a bit more application oriented, I guess. You said that basically data set is needed to conduct these kind of analysis. What if somebody wants to conduct a real-time analysis? What are the tools in your opinion for that?
Real-time analysis, of course, technically speaking, you could listen to the phone calls, but that would harm privacy. So I think that's not allowed. I don't know if that's happening. I meant
on a social network like Facebook, for example, or Instagram, or even LinkedIn.
You can do online analysis, but I don't know of any churn prediction model using the activity on social networks online. I think that's different in fraud. So maybe we can speak about fraud detection, which is a event that goes and that has to be detected online. Churn is not that fast. Let's say the phenomenon of churn, of leaving your provider, is not a phenomenon that advances fast in the sense that you have to do it online. Okay, so in churn you have enough time to analyze behavior and you can decide within a couple of days in order to predict churn. That's different in fraud. So if you want to detect fraudulent behavior, then I think your command is more important, and there are types of analysis where you do online analysis in order to detect fraud. So that would be my answer to your question, to your comment. In churn prediction, I don't know any models that take online data. I think it's not necessary because doing online analysis is much more difficult because it's online. But in fraud detection, we do have to do online analysis. For example, in credit card fraud detection, we have to detect fraudulent behavior during the transaction in order to stop the payment. Okay.
Okay. Well, the reason
I don't know to which answer I replied.
Well, I think it was 50% of the question, but the reason I specifically mentioned churn is because when I was working in the US, I never worked in San Francisco, but what I heard is that when a very good quality developer is trying to find a job and he posts something online, the HR people kind of try to, well, they kind of crowd the space and try to hire him. So I was wondering if this kind of application, for example, if you track the activity of people on LinkedIn of these really specialized tech people, so to speak, if the HR people can use this kind of application to hire, the best talent.
Maybe we should ask Mari. Mari, you're on LinkedIn, as you mentioned before. Did you receive some offers from
yes,
HR
I've received
people?
offers. Yes.
So that's what people do. HR people, they do analyze social networks. Of course, LinkedIn, which is made for this purpose, basically. Yeah, but again, I don't think it's online. Guarang, that was your first question. If it's online analysis, again, hiring people does not depend on the online activity. It's more the profile you leave on the particular social network. Okay?
Yeah.
So that was my example, and now I would like you to work, let's say, 5 minutes in groups. I will separate you in breakout groups on Zoom with two participants in each group. And I would like you to discuss within your group and to come up with other example applications. Again, I did the first job. The first job is, in this case, the easiest one. My contribution is I found that there is a room for social network analysis in churn prediction. In the case of a telco provider, the company could identify customers as nodes, phone calls as links. By doing some social network analysis, they could improve churn prediction models in order to understand better how churn affects the contacts within a social network. Okay? So I would like you to identify the particular area of application, then nodes and links, and the decision, or the decision you take based on your analysis. Did you get the idea before we go into groups? Okay, so I will split now into groups, and we'll be back in 5 minutes from now. And then I would like to ask you to ask some of the groups to tell us the idea you propose. Okay? Okay. Here we go.
Hallo.
Hallo, hallo zusammen. Erik, Tobias, Sie sind angekommen?
Ja, genau.
Ja, prima. Alles klar soweit? Ist klar, was zu machen ist?
Ja.
Okay, ja, dann störe ich nicht weiter. Bis gleich.
Danke, bis gleich.
Hello, Nicole, Calvin, you're still here? You're invited to some groups.
Hello.
Hello, how are you?
I'm good. We're good. We're just wondering, like the comment for the text. What should we do actually? What opinion should we bring to the?
I would like you to identify a particular application where social network analysis could give some additional insight, and then you should identify the particular application, nodes and links, and the decision you propose to take. And there's no wrong answer, okay? So maybe I should have said that before. There's no wrong answer. I want you to think out of the box. So for example, in my case, I mentioned as application area, churn prediction in telco, in telecommunication. Nodes are customers, links are phone calls. That's how I establish the social network. Nodes are customers, phone calls are links. And based on this kind of network, I do some analysis whatsoever. Okay, so I don't want you to do the analysis. I want you to create solutions, to be creative. So maybe you can come up with in my case, the solution could be to improve churn prediction doing social network analysis. I'm not asking you to do it, actually. Did you get the idea, Rafiandi,
Yes.
Anika? Okay, so just let me know if there are still some doubts. Yeah, bye.
Thank you, bye.
Welcome.
There we are back again.
Hi.
Hello. Hello, you're back. Everything back again? Great. So please let me know what's your suggestion for social network analysis? Who wants to start?
We can start, me and Shiksha.
Binodeep, please.
Yeah. So we analyzed viral marketing. So we were thinking about the nodes as the people, such as influencers and all. I mean, the companies also, products also are considered as the nodes. Along with that, we have links as engaging algorithms. Then there are sponsored ads as stories and posts, and the giveaway contest to what the influencers use. And also there are hashtags and stories. So these are all what we considered.
Okay, great. I understood how you build your network, your social network. What are the decisions you propose to take based on your analysis?
Actually, we didn't discuss that on what exactly the decision has to be taken, but we considered like how exactly when we see a platform like Instagram, how exactly it becomes popular based on the algorithms which are quite engaging. Whoever sees that post, they keep getting the similar kind of additional post, and also the companies can get the data and push their ads in between.
Okay, okay, great. By the way, you don't have to select the application from the slide I'm showing. So let me see. That's the slide we have been seeing. That's not necessary to pick from this list. You can take any other application as well. Yeah, but great. Thank you, Binodeep. Who else?
We had the risk in the banking system, which is interesting because I worked for the Schufa once, who's the credit bureau for Germany. So, and I mean, there are different ways you can look at it. I mean, first, I think nowadays, yeah, the central banks are asking who's going bust on their loan. Yeah? And I think the risk in the banking system is also a question who will default on the loan and how big is the volume of money that is lost. So the Schufa, for instance, tries to establish links between nodes, and the nodes are obviously the people who are the loan takers.
Okay.
And the companies, because the vast majority of companies are still private, small private businesses. And if you know that the business is not performing, you could get that also the private person will be not performing or will not earn any money and will default on the loan. Yeah? And if you accumulate that, you will see a number that is actually at risk. Yeah. Another thing is, which would be more sophisticated, which the Schufa can't do, but the banks can do, is to analyze, for instance, where your income comes from. So if you work for BMW, let's take Lufthansa, for instance. If you're working for Lufthansa, or let's say if there are 3,000 euro coming from Lufthansa into your bank account every month, you could establish the link that you're working for Lufthansa. Or you're a shareholder, but let's say you're a worker. So if the Lufthansa is on short labor and if they receive state help, you could say, okay, the risk that this person doesn't earn the full salary or will maybe be made redundant is very high. So if you take these people together, that's a number of money at risk in the system. No?
Okay. Yeah, very good. And decision, I as far as understood, you can anticipate behavior. For example, if they're in risk of receiving their salary, then maybe you could be more careful with loans
applications
you're providing.
Yeah, I mean, at the moment, I think nobody gets a loan. Yeah, but
Yeah.
if you apply for a loan, that's also what the Schufa does. You have a scoring system, yeah. And for instance, you would establish links between certain people. Yeah, if you work for Lufthansa, if you have a doctor title in your name, yeah, the postcode you're in. So you have a combination of social systems you're in where links are made. And from historic data, you could see people with a doctor title are less likely to default on the loan, or professors even less.
I'm not so
or
sure.
if you, well, there's state workers, no? So if you're, at least in Germany, if you're a lifelong professor, I think the risk is very low that you lose your income. If you work as a doctor in a startup, it's a different thing, but I would say an average, yeah, it's a lower risk. Or if you live somewhere in a good area, yeah, and that's basically what they do, yeah. If you have this postcode, you will have a certain risk associated to living in this area. And then they take everything together and they calculate a score. And based on the score, they make the decision whether or not you get a loan and what the interest would be you have to pay for that.
Exactly. Yeah, very good. And any application outside the slide we can see on the screen? So it doesn't have to be just from this list. Any other application?
Hello, Professor. Maybe I could share another application.
Yeah, please, Johnny.
Yeah, so I think, I'm not sure if this is really like I am in the correct direction, but maybe in terms of football, if we talk. So just as we were talking about Lionel Messi, and now let's take, for example, we have FC Barcelona. So maybe in terms of analyzing, we have 11 nodes, and the links between these players are the number of passes that they make. So with
the
number of passes each player makes.
Okay. I
And
like the
this,
application. Very good.
Yeah. And then maybe we depending upon the number of passes that each player makes, we can identify the most important nodes. Okay, and then maybe if I am the manager from some other club, okay, and I am trying to analyze FC Barcelona, and now I understand that these are the most important nodes, and when we play against them, it is important to keep these nodes as passive as possible, and so that will improve our probability of winning the game.
Okay, interesting. And I like the application, not only because it's football, but also because you're thinking out of the box. Okay, and that's the aim of this exercise, to make you think out of the box, to develop the capacity to identify potential applications out there which are not obvious. So the case I chose, churn prediction in telco, that's the obvious case. But I want you to be more creative, to identify, to have the capacity to identify applications that are not obvious. Like, for example, the recipe case. Okay, so it's not obvious that social network analysis could help to analyze recipes or the behavior of football players.
Maybe right, I could, Professor, I could use this for my group project as well, if that's possible.
Please go ahead. Jay, I didn't quite understand you quite well.
Yes, Professor. So maybe I could use this for my group project as well.
The problem is to get the data. I don't know if you will have the data in order to establish your social network.
Right.
Maybe how do you get data describing the passes among players?
Maybe I'll have to watch a complete game of football and look at the number of passes each player makes. But yeah, that will be a bit too difficult and it will go haywire.
But it's possible. No, I don't say it's impossible. It could be possible. The problem is you have to get the data, and it's not enough to just get data for 2 or 3 or 4 nodes. It should be a reasonable number to make sense, because a community within a social network, of course, does not make sense if the entire social network consists of just 3 or 4 nodes. Okay.
Right.
Please let me know your ideas during today and tomorrow. Okay. And of course, you have to convince some group mates. Mari, please.
Just wanted to share an idea. We didn't discuss it because we went according to the list, but I was thinking in terms of Corona pandemic. I think that would be
Great.
an interesting example here, where the nodes are the people or the whole network of people. And let's say that the links are the different similar events that the people visited. And once some of the nodes that are infected by Corona, they become red, and then you can kind of develop or see other nodes that actually could be affected as well, and they should be tested. I think that's actually, I'm sure that social network analysis has been used for these cases, and maybe even the app that has been developed here in Germany, or at least it's used in Estonia.
Yeah, great example. Actually, we have a project working by our national science, financed by our National Science Foundation, where we're working on this. You would call it TTI. Tracing, testing, isolation. Okay, in Spanish it's TTA, but anyway, so it's TTI in English: tracing, testing, isolation. And actually, part of our project is to do social network analysis in the following sense: if we can trace some people that are PCR positive, and we can know how did they behave during the last couple of days. So, for example, they went to school, they took a public transportation, and so on. Then we can kind of understand and predict the spread of the pandemic. So we're working on a project where we will do social network analysis for TTI purposes. Yeah, great example. We started recently, so I don't have results, but maybe I can share some of the ideas we have during this week. There's another comment, Christian, please. Christian.
Yeah, I get another example that might be not that obvious. Like, imagine you have a warehouse with 100 different store boxes, and you want to check how to minimize the distance between getting all the different products from one order. And you can imagine that one box where the products are stored is a node. And then you can see how the products are linked to each other to minimize like common orders and put them all together into one common area. And then like it actually minimize the real distance between the products.
Great. So nodes are boxes or products in your warehouse, is right?
Yeah.
Okay, and links, how do you link 2 boxes or 2 products?
I link them by order. So like if a customer orders something, then this is like a shared link of nodes. Like
that's
he orders product 1 and 5, and then they are linked.
Great, the recipe case, more or less.
Yeah, more or less recipe case applied to a logistics problem.
Exactly. If 2 products go within the same order, then they are linked to each other. Yeah, great idea. Great idea. And the decision, of course, is warehouse layout, something related.
Yeah, that's the scenario. Yeah.
Yeah, great. Again, I don't want you to come up with a reasonable solution. Maybe it doesn't make sense what you mentioned, but that's exactly the idea. I want you to think out of the box. So don't limit yourself by feasibility. That comes afterwards. First of all, I want you to think out of the box. Okay. Did anybody choose gang crime as an example? No? Okay, in this context, I can share some experience we have. We have been working with our police department where we analyze gang crime. Nodes are criminals and links are established by different means. For example, if two criminals or 2 suspects have spent some time together in jail, or if they are neighbors, or something like that. I'm going to present a case during this week where we can understand behavior of suspects in a social network. Everybody of us belongs to a social network. If we analyze the social network of suspects, we can try to pinpoint those suspects that are more likely to commit a certain type of crime. So that's another application in gang crime, where I'm going to share a project with you during this week. So as I proposed with the change of our schedule, today we are in the morning session. We will finish at 9 a. No, sorry. It's my time 9. It's 2 p.m. Okay, so we'll finish at 2 p.m. Right now it's 1 p.m. in Germany. That's right, 1:10. Okay, so we're going to finish in 50 minutes from now, and I'm proposing to have a short break right now. Okay, we'll be back in 15 minutes. For me, it's, in Germany, it's now 1:10 p.m. That's correct?
Yep, correct.
Some answer, please. Okay, thank you, Jan. So we are back at 1:25 German time, and we will finish the morning session at 2 p.m. Then we will have a break of 1 hour, and we will come back at 3 p.m. and finish today at 6 p.m. Okay? So I see you in 15 minutes. Okay, thank you. Bye. Hello. Hello, everybody. We are back now, and let's continue here. I'm going to share the file. Okay, so that's where we finished the first part of our morning session with some example applications. Any questions, comments, doubts so far? No?
I got a short question regarding the limitations of nodes and links. So I wanted to ask, for example, the nodes, is it possible, for example, that there are several types of nodes in a system, so that you, for example, have, I don't know, like companies, customers, suppliers, something like this?
Yes. Yeah, the answer is yes. Those are called bipartite networks, where we have two types of nodes, or could be even more types of nodes. For example, provider and customer. We'll speak about that in more detail. Yeah.
And also regarding the links, is it possible that the links also include some more information? So, for example, to stick with the example of customer and companies, that you see, or that the link includes the information, how much revenue the customer makes per year or something like this?
Yeah, exactly. Think, for example, of the telco network, where I just said, that's what we can see on the screen right now, where I just said for churn prediction, a telco provider could identify customers as nodes. Links are established by phone calls. The advantage is that's the information you, as a telco provider, you do have this information in your database, so it's possible for you to establish the network. That's always an issue. So it's interesting to think out of the box, to invent or to create some ideas, but then you have to realize it. So to build a social network of customers for a telco provider is possible because you do have the phone call information. And now I'm coming back to your question. It's not only to establish a link if there are phone calls. You can establish also the strength of a link. For example, by frequency, how many phone calls do I have in my database between customer A and customer B? So for example, frequency of phone calls and or length of phone calls. Those are additional data that could help you to establish the particular network. So the answer to your question is yes. There is some information that goes beyond the simple creation of a link. You could have frequency of interaction, strength of interaction, and so on. Did I answer your question?
Yeah, perfect. Thank you.
Okay, great. Thank you. Anything else? Also regarding organization of the course, evaluation, maybe during the break you came up with some doubts. Any other questions so far? Okay, great. I should start recording again, which is on hold. So we are recording again now. So let's continue. Now that we have some ideas of social networks, we're going to introduce basic concepts. First question is, how can we represent formally a network? Then we're going to speak about the importance of nodes in a network and the strength of links in a network. And that's exactly the third issue. Links is exactly related to the previous comment. Okay, so how can we identify strong or weak links? It's not sufficient to say there is a link. We can also define the strength of a link. Okay, I think that's what we will see this afternoon in the afternoon session. Okay, so first question is, how can we represent a network? So that's one way how we can represent a network, by just drawing the network. We have nodes and links. In this case, we have a directed graph. That means there is a direction between node 4 and node 3 applications where we have direction with regarding the interaction. in which case do we have direction of this interaction? Mr. Ye, I can see you on the screen here. Do you have an example where the interaction has a direction where it goes from 4 to 3, like in this case, for example?
4 to 3, yeah. Goes from, okay, for example, if it's a money laundry, if the notes are the accounts and the links maybe are the transaction of money, so it has a flow direction.
Yeah, very good. Transaction, money transaction goes, for example, from 4 to 3, or phone calls. 4 is calling 3, or retweets. Okay, so those are some examples where the interaction has a directionality. Okay, goes from A to B. How can we represent this network? So for example, there is the concept of an adjacency matrix, the one we see at the bottom here. So for each node, we have a column and a row, and we have a 1 in cell ij if there is a link that goes from I to j. For example, we observe a link that goes from 1 to 2. That means in position 1, 2 of the adjacency matrix, we have number 1. 1 means there is a link with this direction, in this case from 1 to 2.
Sorry, is it just me, or I'm just seeing the old slide still, or?
Yeah, I think
Yeah,
that's
it also
for me as well.
freezes.
Yeah.
The slide stops at the example application.
Sorry?
The slide stops at the example application, sir. So we didn't see the latest slide.
Okay. Sorry for that. Let me see how to fix it. What do you see now on the screen?
Still the example expert.
I think you have to stop screen sharing and then start it all over again. Then it should work.
Yeah, looks like. Because I'm sharing another screen.
Or are you in presenting mode? Because then you have to just click back on the presenting mode when you.
So do you see now network representation?
Yes.
Yeah.
Okay, great.
Yes. But this is your
Great.
PowerPoint. Huh? It's not
Yeah, it's my PowerPoint, which says network representation, and we see here a directed graph.
Yeah.
Yes.
Now it's the presenter. Now it's the presenter mode again.
Yeah. So you can see this graph with 4 nodes.
Yes.
Yeah.
Okay, great. Thank you. So how can we represent this graph? One way for, let's say, readable for humans is the graph itself with nodes and links, and we can interpret it. But a computer doesn't have eyes. A computer doesn't see it the way we see it. The way we can tell a computer the structure of a network is via the adjacency matrix, the matrix we can see now here at the bottom of this slide, where we have rows and columns representing the nodes. So in this case, we have 4 nodes. Each node is represented by a row and by a column. And if we observe, for example, a link from 1 to 2, like in this case, from 1 to 2, we have a number 1 in position 1, 2 in our matrix, this one here. Okay, so in general, in position ij, I do have a number 1. That means there is a link that goes from node I to node j, like in this case, from 1 to 2. Since it's a directed graph, we don't have necessarily a link from 2 to 1. That means in this case, in this position here, we have a number 0. This means the adjacency matrix is not symmetric. And in the diagonal, there is no information because we are not interested in links from node 1 to node 1 between among the same nodes. Okay, so that's the adjacency matrix. That's the way we tell our computer, we tell our models how to represent a graph. In the case of a directed graph, examples are, as Mr. Yi said before, money laundry, money transactions, for example. Node number 4 sends money, deposits money in the account of node number 3. There is a direction. That's different, okay? That's different in the case of an undirected graph. Which case of interaction can be modeled without considering direction? What does it mean? There is a relation between 3 and 4, but no direction. Any example?
For example, if the nodes are people, we can just say that, and if the links are, if they know each other or not, if they have any contact, we can think it like that. So when 2 knows 3, 3 also knows 2, kind of thing.
I'm sorry, I couldn't hear you quite well. Could you say it again, please?
Can you hear me now?
Excuse me, say it again, please.
Can you hear me now?
Yeah.
Okay, so for example, if we think about this as a normal social network, and if we think that 2 and 3 are people, and the links are if they know each other or not, we can think it like that. For example, if 2 knows 3, 3 also knows 2, so it's an undirected graph.
Yeah, exactly. Knowing each other does not have any direction. Or being neighbor. Yeah, 2 and 3 are neighbors. They're living next to each other, being neighbors, or working in the same company. Those relations establish links without direction. In this case, we also use the adjacency matrix to represent formally the social network. In this case, of course, the adjacency matrix is symmetric. If 1 is neighbor of 2, then 2 is also neighbor of 1. You can see here we have a symmetric matrix since it is without any direction. Okay, the adjacency matrix is an important tool in order to represent a graph, and we will see several applications based on the concept of an adjacency matrix. Okay, so that's the different way how to represent the data. On the left side, the left-hand side, we have, let's say, classical view on data. We have customers, people in our rows. Those are the observations. And in the columns, we have features describing our customers. The adjacency matrix on the other side is a symmetric matrix where we represent the relation among nodes of our network. Okay? So now let's turn to the next question, where the idea is to determine importance. How can we determine importance? Think of a social network of your choice, and what does it mean a node is important? And here are many answers. You can see here Piyush Kulkarni on the screen. Piyush, what do you mean? What does it mean a node is important?
Well, a node could have, when we say like the important nodes, like for example, through which we can, for example, in talking in terms of business, we could that would be the point where we could increase our sales or kind of increase the profitabilities or kind of have different matrices or KPIs. So that could be an important node. So for example, a sales channel where we could, pour more money into getting more customers or something like that.
I understand you're arguing from an application point of view, but for the moment, I would like to argue from a social network point of view. So we just introduced the representation. So think of a network like this one here. What does it mean? A node is more or less important. So Christian also raised.
Yeah, maybe so. Let's say the node through which we have multiple links passing by could be defined as an important node according to
different links. Actually, that's the first measure, degree centrality. We just count the number of links. That means a node is important if it has many if it is adjacent to many links, to many other nodes.
Yeah.
Yeah, that's the first concept, but it's not the only one. Yeah. Christian Meyer, please.
Speaking of a basic example, it's like if you look at your smartphone and the context you're writing to, the longer you or the more often you write to someone, the higher a person gets into your contact list or list of suggestions who you want to write to today. And basically the frequency of messages you share with someone can be the importance of nodes in your like very social network life on your very own smartphone.
Yeah, you speak about interaction. What does it mean that you get more importance as a node in a social network?
More important in terms of more like visible. The amount of transactions or the amount of links gets
yeah, that's similar to what your classmate said before. That's the number of links. That's correct. Yeah. But think of the following question. If you have many links, but you have many links to nodes that are not very important. So maybe it's better for you to have less links, but to more important people. Does that sound reasonable to you, Christian?
Yeah, I understand, yeah.
Okay, so that's the eigenvector centrality, which takes into account the importance of other nodes. So the first measure is just counting nodes. Sorry, the first measure means just counting links. A node is important if it has many links. Then the eigenvector centrality says it's not sufficient to have many links. You hopefully have links to important nodes. In between, we have the closeness centrality and betweenness centrality. We'll go into more detail. And finally, we will speak about the PageRank algorithm. Who knows who invented PageRank? Google, yeah. I think most of us know it. And of course, everybody of us uses every single hour of the day the PageRank algorithm or some, let's say, modified version. Yeah, the Google search engine uses PageRank algorithm and of course a more sophisticated version than the one that was presented in 1998. Okay, so let's go step by step. We have degree, betweenness, closeness, and eigenvector centrality, and then PageRank, 5 measures that determine the importance of a node. And I also present here some additional web pages, YouTube videos explaining these centrality measures, and also an article with the link on Springer. That's an article where you can find more information on the importance, a critical review of measures, but also a web page where you have R code for network centrality. Yeah, there you can find an introduction and also R code to calculate the network centrality. But let's go first into the concepts, and I'm going to start with the degree centrality, and that's the only thing we're going to do before we have our morning break, our lunch break. It's 8:45, 8:45 for you. We will finish 1:55, okay? So degree centrality, what does it mean? A degree centrality of a node is just the number of links it has. Of course, we can separate between in degree and out degree in the case of a directed graph, but in the case of an undirected graph, there's no difference. It's identical in undirected graphs. For example, in the graph we can see here, we have associated to each node a number, and this number is the node degree. For example, node 1 has degree 2 because it has 2 links. Node 2 has degree 3, it has 3 links. So this way we can establish the importance of a node by just counting the links it has. In this network, node number 4 is the most important node regarding degree centrality because it has the highest number of links. And node number 7 is the least important because it just connected to one other node. Okay, degree centrality, just counting the number of nodes. What else makes a node important? So it's not just counting links, there's something more to node importance. Try to criticize the notion of degree centrality. And again, I want you to think out of the box. So I'm presenting here something, and I want you to criticize it. In which case, the degree centrality fails. In which case, could you think of an example in which case something else makes a node important, not only the number of links?
The quality of the node. I mean,
very good, very good.
Friendships. If I think in social network thing, it's not the amount of Instagram followers, but maybe the amounts of posts or the quality of the posts that you do.
Okay, Christian, you said the quality. That's something we're going to capture in the eigenvector centrality. The first three measures, degree, betweenness, and closeness, are just based on links. And they don't care about the quality, as you said, or the importance of other nodes. Eigenvector centrality, as well as PageRank, take into consideration the importance of other nodes. Very good. But something else. So I need another answer in order to switch from degree centrality to betweenness centrality. The fact of being in between could make a node important, even if it has few links. Ideas? What does the concept of betweenness capture?
Maybe also the intensity between.
Say it again, please.
Maybe also the intensity between two nodes. Like just because they share one link doesn't mean that this link is less intense. It goes more into a qualitative statement, but it does not weight like what the link actually is.
Okay. Typically, the intensity of links is not considered as being a measure for the importance of nodes. I'm not saying it's not useful, but
maybe it's the way how they bridge different people in the network. If you think of traders or of shops, for instance, who
very good, and that's exactly what we measure with the betweenness centrality. So we can say there are two communities that are not very highly connected, but there is one trader, as you said, that connects those two communities. So this node could have few links, but it's important because it's connecting two communities. And that's exactly what we're going to see with the betweenness centrality. Okay. So in order to define the betweenness centrality, we need the notion of a shortest path between two nodes. So let's introduce first the notion of a path and shortest path between two nodes. And those are basic notions from a graph theory. A path between two nodes is simply a sequence of nodes and links connecting those two nodes. For example, a path from node 2 to node 5 is 2, 4, 5. That's one path from 2 to 5. Another path from 2 to 5 is 2, 1, 4, 5. Or the other example we have here, 2, 3, 4, 5 is a path between 2 and 5. 2, 3, 4, 5. That's a path from node 2 to node 5. A shortest path between two nodes, well, has to be a path, but a path with the minimal number of intermediate nodes. And again, we have the notion of distance. So a shortest path has few intermediate nodes. For example, 2, 4, 5 is a shortest path between node 2 and node 5. Important here to mention this word a, the shortest path, is in general is not unique. There could be several shortest paths between two nodes. Yeah, for example, the shortest path from 1 to 3 is not unique. There are two shortest paths, 1, 2, 3, or 1, 4, 3. Another path would be 1, 2, 4, 3, which is not a shortest path from 1 to 3. Okay, you got the notion of path and shortest path? It's important. If there are doubts regarding these two concepts, please mention it now. Okay, Christian, please.
Sorry, just a question. Doesn't both concepts correlate with each other? The more like links I have, the shorter the path in general. Isn't there a correlation between both?
You're saying a node with many links has, how would you continue the phrase?
A node with more links tends to also have a shorter path between the nodes, since it's more connected.
I think it's not well formulated, the question you raised. A node with many links does not speak about connection. It addresses just the node itself. It does not address the connection of this node. I could think of a node that is far apart with many nodes in a small community, but not very well connected. I got your point. You're saying, you're not saying it's identical, you're saying it's correlated. I don't know, I don't think so. Of course, if you have many links, yeah, that's related to the next measure, closeness centrality. Christian, I think there I would like to come back to your remark in the context of closeness centrality, but in betweenness, I don't see necessarily a high correlation. But let's introduce it first. Okay, so we introduced the concept of path and shortest path, and having done this preliminary work, we now can define the concept of betweenness. And think of a social network where you have nodes, and I want to calculate the betweenness centrality of node V. Okay, so this formula takes node V, any node of my social network, and it calculates the betweenness, the degree of betweenness of node V. So node V could be, for example, node 4 in our example here. Okay, so for node 4, I'm calculating this expression. And what does this expression mean in words? I take all shortest path from S to T that go through V divided by all shortest path from S to T. For example, I choose S and T as two arbitrary nodes. Okay, so S is a node and T is a node. For example, again, we are calculating the degree of betweenness of node number 4. So V is now 4. And now I choose any combination of two nodes in our network. That means I choose S and T arbitrarily, any combination. So S and T could be 1 and 2, then 1 and 3, 1 and 7, and so on. And here I have a ratio. This ratio basically means what I'm showing here in words. In the nominator, I have the total number of shortest paths that go from node S to node T and pass through node B. For example, let me continue first. In the denominator, I have the total number of shortest paths that go straight from S to T. For example, I choose S equal to 1 and T equal to 2. The shortest path that goes from 1 to 2 is 1. That's the number of shortest paths. That's my denominator. Okay. And the nominator is the number of shortest paths that go through 4. The nominator is 0. So if I pick S equal to 1 and T equal to 2, then I have here 0 divided by 1. If I take S equal to 1 and T equal to 6, then I have the number of shortest paths that go through node 4 divided by the number of shortest paths. And in both cases, it's 1. The number of shortest paths that go through node 4 is 1, and the number of shortest paths from 1 to 6 in general is also 1. Okay, so that's the calculation we have to perform here, this ratio, and basically it's taking into account how much my node B connects to communities. So let me switch to a whiteboard. Just a second, please. Let me open a whiteboard. Here we go. You can see my whiteboard, which says September 14.
Yeah.
Okay, thank you. So that's what I prepared for the PageRank algorithm. But before PageRank algorithm, let's see an example of betweenness. Okay, so those are nodes. Okay, those are nodes. Let me change color. Links are red. So I have a social network with nodes and links. So basically, what I'm saying is there are two communities, one community here, one community here. In black color, we see nodes. In red color, we see links. And now let's go back to one node here. So this node here, sorry, this node, we call it node V, okay? And this node has a low degree centrality. Its degree centrality is 2. It has just 2 links, okay? But it connects 2 communities. So node V has a low degree centrality. Its degree centrality is just 2, but it has a high betweenness centrality. Why? Because it connects nodes from both communities. Okay, so if we take, for example, node S here and node T here. So the shortest path from S to T has to go through node V. Okay. So I'm sorry, we passed already the time. It's now 2 p.m. in Germany. Let's have a break, 1 hour, and we will continue right here to define well the degree, the betweenness degree. Okay, I think we got already some idea, but I think we have to get a better understanding of the betweenness centrality. Okay, so we have a break now, and we're back in 1 hour, 3 p.m. Okay.